And welcome Calculus 3 students. Today we're looking at the divergence theorem, and if you'll remember, the divergence theorem is a three-dimensional version of the flux form of Green's theorem. So in going through the divergence theorem, we find that we could do just the triple integral and still get that same result. So we're going to verify in example 1, we're going to look at our sphere that we've looked at before, and we're going to verify that we're going to get that same result. All right, in the first one that we're going to do, we're just going to do it using the triple integral, and we'll take our partials and then we'll substitute into our triple integral and we'll get 4 pi a cubed. Going ahead and parameterizing it, what you'll end up with is first up, what you had to do is just parameterize it so that you can get it in polar coordinates, and then we're going to do it using the double integral. You still have to do your normal and then do the dot product of that normal, and when you do, you will find that you get the 4 pi a cubed. So we found that in either case, using the triple integral or the double integral for the divergence theorem, we still get that 4 pi a cubed. In our example 2, we went to find the divergence here, and we found that the gradient dot product with our vector field here, we get 0 for this one. So in this particular case, we should note that the flux across the hemisphere is 0. So we have an interesting note here that pure rotation fields of the form where your unit field vector or your field vector is A cross R, they'll have 0 divergence. In example 3, we need to compute the surface integral involving the 6 faces of a cube. That's basically what you have described here. And for that, we're going to have to get my dot product. So, all right. So in taking these partials with respect to my x, y, and z, what I end up with is the following. And the next thing I'm going to need to do is set up my triple integral. So my triple integral, let's just go ahead and plop it down, is going to just be that gradient dot product with that field vector, triple integrated over that volume, and nice limits of integration here from 0 to 1, and evaluating that integral, you'll see that you get 3/4. So the net outward flux is positive. Next, we're looking at divergence using mass transport, kind of like viscosity if you're talking about mass moving, and how to calculate that mass transport using that divergence. So this is a formal derivation of that net flux out, and this is just that triple integral of the gradient dot product with that field vector, which is what we looked at before. We're going to look at the divergence theorem for hollow regions, meaning that we're taking a part out or a part away. Notice the subtraction sign here, so you do the outside minus that inside, that is the hollow part. So we're going to look at the flux for an inverse square field, and we need to, in A, find the net outward flux across that surface. In our A part, what we're going to use here is a result that we found in section 15.5 when we had our p equal to 3, if you might remember that example that we did in the couple of previous sections. And what this is telling us is that our net flux across S is 0 if we're just looking at the net outward flux on this region. In the B part, we're going to find the outward flux of F across any sphere that encloses the origin. Alright, so we'll need to make a few assumptions, and here we go with the B part. Notice that we're going to say that the flux in equals the flux out. We're going to need to calculate one of them, so we go straight away and just go with the hollowed out portion, the N1, and just substituting for what we have found before, and then integrating, we will get 4 pi. This last bit is just an explanation of Gauss's law and the permittivity of free space, and just goes through that derivation and how we use that divergence theorem in the calculation, in the derivation of this permittivity of free space. And then the last slide is just a summary of the different theorems that we've gone through in this calculus sequence. Fundamental theorem being covered in Calc 1. And it's been a blast. Let me know if you have any questions.